Hi everyone, welcome to Om Learning Lab. In this video, we are going to learn about multi-head attention and positional encodings. Now, I would highly recommend people to go through the first video, which is an explanation on what the attention mechanism is, how it works on the encoder side. I went through all the math in detail and tried to make it easily understandable. So that would be a prerequisite to be able to watch this video, to be able to follow the content of this video. So I would request people to go ahead and watch that first, then come back to this video and continue. Now, coming to this video, we will cover these two topics, multi-head attention first and positional encodings. The reason being that both these topics are extremely important technical details which are a part of the transformer architecture. Now, if anyone remembers, in the first video I covered about the encoder side, how attention works in encoder, but I just covered attention mechanism in its most basic form, like mathematically and intuitively what attention mechanism looks like. Now, exactly what multi-head attention does, how it is different from the attention covered in the previous video, why is it important? Those are the details that I'm going to cover in this video. Along with that, these couple of things, positional encoding, are like this is another additional detail which is also going to be covered in this video. Without any further ado, let's get started. Now, what I have mentioned here is directly taken from the paper. This is mentioned in the paper by the authors regarding what multi-head attention is all about. Now, what does it say? What does this math say? Now, what were we doing in attention mechanism if someone remembers from the first video? So basically what we had was, we can just go back to that example that I had taken, example sentence, which is Henry likes to play football. This was our sentence. And of course, we can use any embedding method to create vectors for each of these words. So we'll have 5 embeddings with us. And we can have our X matrix, which is the input matrix. It would have 5 rows. This would be 5 rows. 1 row representative of each word. And assuming that we have 4-dimensional vectors here, that is not the practical case, but just for simplicity's sake, assuming that our vectors have dimension 4, so we'll have 1 by 4 vectors representing each of the words. Now, if anyone remembers, what we are doing is we are projecting them into 3 spaces. One is the query, one is key, one is value. Details regarding this are covered in the previous video. So again, if someone is not able to follow this part, please go back and watch the first video, then come back to this position. Now, this was what we are doing, right? So we are projecting into these spaces to create query, key, and value matrices, and then we are applying, like basically what we are doing was effectively this. So query multiplied with key transpose divided by the square root of dimensions, finally multiplied with value. This is effectively what attention mechanism is doing, right, to get the final vectors. Now, the idea for multi-head attention is what they are saying here: concat head 1 up to head h, then multiply it with some additional matrix, where this head I is the result of attention mechanism passed on this. In other words, the idea is, what if we have multiple projection subspaces? What does that mean? What it means is our results or the quality of result that we get by doing all this attention mechanism effectively depends on these 3 matrices, right? These 3 matrices which are going to be learned by the model during the training process. How well these matrices are, how well they project the input embeddings into the query, key, and value space effectively it would basically decide how well our model is, how well the attention mechanism works. So the idea for multi-head attention is, why don't we use multiple projection subspaces? I mean, why don't we use, instead of just WQ, WK, WV, why don't we have W naught Q, W naught K, and W naught V? For example, this is the first set of projection matrices that we have. Similarly, we can have W1Q, W1K, W1V. This is the second set of projection matrices, so on and so forth, till WH minus 1 Q, WH minus 1 K, and WH minus 1 V. Remember, we have, like, as per the paper, we have H number of heads. So each head basically represents a separate projection subspace. And projection subspace means these three matrices, okay, which are going to be learned by the model. Because in the end, how well we learn these matrices, the values of these matrices would determine how well our model performs, how well we attend, how well our attention mechanism works, basically, how well we are able to attend to different parts of the given input sentence. So each head represents a subspace, and a subspace is these three matrices. And since we have H such subspaces, and starting from 0, so it will go till H minus 1. 0 till H minus 1 is H subspaces. Alright. And what's important now is, each of these subspace would carry out the attention mechanism independently, as if they're independent. So everything would be exactly the same. Here, originally we are saying that the output is, let's say, some matrix Z, which is represented by this. Here we can say Z naught would be soft max of, I'm just writing soft for short, multiplied with Q naught times K naught transpose divided by the dimension square root for normalization, dot product with V naught, where this Q naught, K naught, and V naught would be the projection of input matrix using these matrices. I mean, what can I say? Q naught would be X multiplied with W naught Q. K naught would be X projected using this W naught K, and V naught would be X projected using W naught V. So those projections would be used exactly as we do in normal attention mechanism to get the first set of outputs. So Z naught is basically the output for first projection subspace. Like, attention mechanism has been done for the first projection subspace, and this is the output. Now, why this is important? That initially, when we initialize the matrices, I mean, the model has to learn these matrices, right? That's the whole essence of the training process. So how we initialize these three subspaces is important. And there is no guarantee that, let's say, we just choose a single subspace, the initialization is correct. Maybe the initialization was not that accurate. And in the end, whatever the model learned through the process was not that great. So it kind of makes sense to have multiple such subspaces, multiple such initializations, because that effectively would increase the chances that eventually during the training process, the model was able to learn the effective weight matrices in some projection subspaces, and that information would be captured. Now, of course, the question that would be coming to people's mind is, how exactly do we capture that information? Because, optimal information could be in any one of these subspaces, right? Or a combination of these subspaces. So the whole argument is, if we have one subspace, maybe the information captured is not correct. So let's have multiple subspaces so that the chances that information captured is better or richer, so to speak. But how do we know that which particular subspace or which set of subspaces have the best information? Well, what we can do is, so similarly for this also we'll have Z1, which will be softmax of Q1 times Q1 transpose, blah, 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 whatever the function is. And all the way we'll have up till Z times H minus 1. So you'll have H outputs for H attention heads, right? That's what they have defined. So head basically means, attention mechanism performed on these matrices. right? Okay. Now, what we can do is, if we have, let's say, H outputs, H attention heads, the paper suggests concat all of them and take their multiplication with some matrix W naught. Okay, I would repeat this. So initially, when we are just having one projection subspace, the problem that uh, we encounter is that, you know, we are not, so it's not a problem per se, but the process is we do the attention mechanism, we get some matrix Z, which is the attention output. Here we have H attention outputs. We are not sure which set of outputs have the best set of information. So what we'll do is we'll concatenate all these results. So for example, in our case, our X had 5 sentences. It was a 5 by 4 matrix. Let's say after doing all the attention operation, we get a 5 by 3 matrix. I mean, that's what we were doing in the first video, if someone remembers. So the Z naught would be a 5 by 3 matrix, right? So it would be 5 by 3. And this Z1 would also be a 5 by 3 matrix. All the way up till Z H minus 1, we'll get 5 by 3 matrices. Now, what we'll do is we'll concatenate all of them. So if I concatenate all of them, the number of rows would remain same. I mean, we would just stack them. We'll just stack them in this fashion. You know, though, so the word meaning remains intact, but for different subspace, we'll just stack them. It's just column stacking. So if we stack them column wise, what will happen is ultimately our matrix would be 5 in row, 3 times H in the number of columns, right? Because the first 3 columns is the representative of Z0. The next set of 3 columns is representative of Z1, on the way up to the final, the last 3 columns are representative of ZH minus 1, or the final attention head that we have. Now, once we have this, we can have a separate weight matrix of dimension 3H upon 3, which can also be independently learned by the model. And when we do this multiplication, 5 times 3H matrix multiplied with 3H by 3 matrix, ultimately we'll get a 5 by 3 matrix, as we are getting in the original attention mechanism. So that will be the final output, and we are done. So we have 5 embeddings for 5 words, and each of them have dimension 3. This is exactly what we wanted, what we're doing in the original attention mechanism process as well, and we have arrived upon it. So this is in a nutshell what the multi-head attention process is all about. In short, the idea is a single subspace might not be a good idea. So let's just introduce multiple subspaces. For each subspace, we'll have these 3 projection matrices. We'll generate the query, keys, and the value vectors by projecting the input using those projection matrices. Once we have those particular vectors, we will carry out our attention mechanism business as usual and get H results, H attention vectors or matrices, which will be called attention heads. Then you concatenate all of them column wise. So effectively you will have, for each word, you will have column stacked embeddings. So the first 3 represent the first attention head, next 3 is the second attention head, so on and so forth, till the H attention heads are over as represented here. Then you can like learn an independent matrix W0 or W0, whatever you want to call it, which has the required dimension, so that once we multiply the stacked attention output results with that, we get the desired value, the desired dimensions that we require. And this is something that we can learn, our model can learn. Right? So of course the advantages are, since we are using multiple subspace, the chances that we get better attention results is increased. And for each word we have more information. So for multiple initializations, for multiple projections, we have information captured here. And this is also something that can be learned, and we can have a good representation for this to ultimately get a better possible outcome, so to speak. which takes multiple things into consideration, multiple subspaces into consideration. That's the whole idea. I mean, take more and the chances that you get better results improves. That's it. At least that's what I could understand. That's all. Okay. Now, that is about the attention mechanism. And having completed this, we'll move now to the next part, which is positional encodings. Okay. So let me just write the topic here. Positional encodings. Positional encodings. Okay. Let's go back to our example sentence for a moment, which was this: Henry likes to play football. Now, as human beings, we know which word should follow which. In other words, we have a sense of grammar and grammatical rules. What I'm trying to convey here is we have some idea about the syntax, about the ordering of the words in the given sentence, so that it conveys the relevant information. However, for a machine, for a computer, ordering is purely based on numbers. I mean, computers don't understand text, right? That's the whole point of natural language processing. We have to convert them into text. How efficiently we convert them into text is what the research is all about. And since computers understand numbers, somehow using numbers, we have to convey ordering information to the computer. Because so far, what we have done is, all we're doing is, we are trying to convey importance values to the computer through the attention mechanism. I mean, what we are doing is, we are sending we have this particular embedding matrix, and through all this attention process, even by using multi-heard attention, we are trying to teach the model how much attention it should pay for a given word in context of a given word to other words. Now, one important factor here would also be that in which order do the words appear? What is the importance of orders? What is the similarity between the words? I mean, is there any similarity between to and play in relation with the order? If we talk about syntactical importance, syntactical similarity, then if anyone can recall from the first video, play would most likely have more similarity with football. I mean, the person likes to play what? He likes to play football. Who likes to play something? Henry likes to play something. I mean, syntactically speaking, these words, play is likely to have more relation with football and Henry rather than to. I mean, this is just an intuitive example that I'm trying to give here. But the point that I'm trying to pass across is, apart from this information, that in context of a given word, which other words are important, where we should pay more attention to, we also need to pass this information to the model somehow, that this word is coming after to. I mean, the ordering is important. So how do we do that? For that, we use positional encodings. So if I represent the given matrix, given input matrix X as a 5 by 4 matrix, where 4 is the dimension of the embeddings that we have. Let's call it W11, W12, W13, W14, just following upon the convention that I used in the first video, so on and so forth. Then the idea is that don't just directly send this X to the whole attention process that has been described above. Rather, you also add a time signal to it, a timing matrix, which would also have the same dimensions. It would also have 5 by 4 dimensions, because we want to add two matrices, so their dimensions must match. And this timing matrix would be something like T11, T12, T13, T14. And I mean, basically for every word, we'll have a timing embedding as well, a time embedding as well. And this information is regarding the relative ordering of the words in the input sentence. That is the information that we want to pass to the model to not only be able to understand where it should pay more attention when it is looking at a particular word. So which part of a sentence should more attention be paid to? Not only the model learns that, but it also takes into account the relative ordering of the words, how the orders appear. So that's why we use positional encodings. We add this encoding, the positional encoding time signal to the input embeddings, so to speak, and we get some output matrix X dash. This has the uh, positional encodings embedded into it, and then we pass it to the normal attention mechanism. So the obvious advantage is the model has the time information. Now, of course, there will be one important question that how do we decide this timing information? I mean, is there any fixed process that this is how we generate the timing matrix and that always works? The answer is for this particular paper, the authors have used sinusoidal waves to generate the timing matrix. So I'll not be going to the exact mathematical equation, but roughly speaking, they have used something like sine position. Sine position, and if I remember it correctly, it's something like the position of the word is important and the dimensionality is important. So for this video, for understanding purpose, all that suffices is to know that a sinusoidal wave function has been used by the authors to be able to build this timing matrix. Why they have used it is because it was their hypothesis. I mean, there is no concrete proof that that's correct, but it's their hypothesis that they have mentioned in the paper that, if we take sinusoidal functions for generating the timing matrix, relative positions can be captured better. And in fact, we don't exactly have to always use the sinusoidal function to generate this timing matrix because that's a fixed way. So we are basically saying that, hey, you know what, this timing matrix that we need to add to the input, it's a fixed choice. We don't have to do that. This can be learned as well. I mean, we can just ask our model to learn all these timing bits. That's also a possibility. And as per the paper, they have experimented on that way as well. Or at least they are sure that if we use sinusoidal wave functions to get the timing matrix, the results are comparable with what we get if we use learned weights. So there are two ways to generate the timing matrix. One is learn weights, ask the model to learn these weights, or you use sine functions. And both these have really comparable results. And the reason for using sine function, as mentioned by the authors, is that they hypothesize that it captures relative positions better. And in simpler words, what they mean to say is if we are taking sine of position, let's say where position represents, let's say the absolute position of any word in a sentence. So, for example, if a particular word was present at position, let's say t. So let's say this is word number 1, word number 2, word 3, up to I'm talking about the tth word. So let's say in position number t, we had some word. And for this, the information, the timing information is something like sine t, let's say. And let's say after k position, the position is t plus k. For that, the representation would be sine t plus k, right? This is just roughly I'm trying to explain to give some intuitive idea. Of course, when we actually implement it in code, there will be subtle differences because theoretically something being correct and being able to implement that practically, being able to scale that practically, they are different things. But for understanding purpose, this should suffice. So for the tth word in the input sequence, whose position is t, will have this timing signal. And for t plus k, we'll have this. But this is basically, if we try to expand, so sine a plus b is sine a cos b. So sine t multiplied with cos k. Now remember that this k is just a shifted value. So it's basically some multiplier multiplied to the original signal that we had, plus its cos t times sine k. So here sine k is the constant. Now cos t is same as sine pi by 2 minus t. So in other words, when we look at the timing signal for a shifted word, we basically get the same signal that we had with some constant multiplied to it, plus the shifted version of the original signal with some constant multiplied to it. In other words, it's in some way a linear combination or a linear projection of the original timing signal. So we can say that relative position information is captured because it has this term in it and it has this term in it, which is basically the shifted version of the original signal. So roughly speaking, that would be the idea. So that's why positional encodings have been involved, and they have been involved in both the encoder and the decoder pieces. So the idea is, along with asking the model to learn to compare one word with others and learn where it should pay maximum amount of attention to, it should also have some idea about the relative ordering of the words, because in the end it's a machine, it doesn't know grammar. We have to teach it through numbers. So that's why you add a timing matrix and then pass it through attention. How do you create the timing matrix? Either you ask the model to learn it, learnable weights, or you can use a sinusoidal function as mentioned in the paper because they have comparable results. And the idea being that if you use sinusoidal functions, the relative importance, like there is like what to what timing signals will have some linear relation between them. So that information would be better captured. The relative ordering would be better captured by the model. That's the idea. So that would be all from my side for this particular video to explain what multi-head attention is and what positional encodings are. These are two, concepts, technical concepts that need to be understood at least from an outer level, from an upper level, or from a higher level, so to speak, in order to be able to make sense of what's going on, how they're important in the overall transformer model architecture. In the next video, which will be the final video in understanding the transformer architecture, we will cover how the decoder works. So far we have understood when we have some sentence input embeddings, we do positional encoding on them. Why we do that? We pass them through attention mechanism to be specific multi-head attention. Why multi-head attention? How does it work? How does attention mechanism maps works at each level for each representation subspace? We have seen that, and we are quite clear what we get as the output. But how do we use that? So we have attention vectors as the output after passing them to this encoder. But how are we going to use that to serve our purpose? We'll see that in the decoder segment, which will be the next video. Stay tuned. Meet you there. Thank you.